Hello. Now today we're going to look at stationary points, which would be the maximum or minimum that we've already talked about in functions, and we're also going to talk about points of inflection, and we'll get to what they mean in just a moment. A quick recap of what we know about our derivatives and our second derivatives. If dy dx is greater than 0, we know the function is increasing. Now if we get d2y dx squared, the second derivative, that's how the slope is changing as x changes. So it's the rate of change of the rate of change, the rate of change of the slope. If that's positive, that means the slope is increasing. It's becoming more positive. If dy dx is less than 0, the function is decreasing. We have a negative slope to our function for those values of x. And if d2y dx squared is negative or less than 0, the slope is becoming more negative or decreasing. That doesn't mean we have a negative slope. It just means that the slope as it's changing is becoming more negative. It's decreasing. And we know that when dy dx is equal to 0, we have a turning point. Now, there are several different names for when dy dx is equal to 0, and we need to know them because they can come up in exam questions. So a turning point is a name for dy dx equals 0, so is a stationary point, or we could just directly be asked for the maximum and or minimum point of a function. And all of that means we're looking for where dy dx is equal to 0. And finally, our point of inflection is where d2y dx squared, our second derivative, is equal to 0. And the significance of that is, if we look at our cubic rough sketch that I've got going here, the slope of the tangent to the curve at my maximum point, my dy dx, is equal to 0 because I have a horizontal line. At my point of inflection, my POI, point of inflection, what has been happening to the slope? Well, it was 0 here. It starts out positive, it goes to 0, then it becomes more and more negative. We now have a negative slope as we're in this part of the function. So we started positive, we went to 0, or end up negative. We're becoming more and more negative as we come down to our point of inflection. But what happens after our point of inflection? Well, now our slope starts to get more and more positive back to 0. So we have our slope of 0 at the minimum point. And then our slope becomes positive and keeps on increasing and increasing. So what's happening to the second derivative as we change our values of x? Well, here, the second derivative is negative. It is becoming more, our slope, our red line, is becoming more and more negative. After the point of inflection, our slope becomes more and more positive. So the point of inflection is where we change over from dy dx becoming more negative, the slope becoming more negative, to where it starts to become more positive. Or vice versa. It could be where our slope was positive and its rate of change was positive, and then it becomes more negative. So the point of inflection is where we change from the slope becoming more negative to the slope becoming more positive. That's our meaning of our point of inflection. Now, what is a consequence of that is, at the maximum, if we're finding a maximum, as we often will be, dy dx is going to be 0, and d2y dx squared is going to be negative. It's going to be less than 0. So if we find our maximum point when dy dx is equal to 0, and then we sub in that x value into d2y dx squared, we should get a negative number, because our rate of change of our slope is negative. As we're going over this hill, we're becoming more and more negative in our slope. And contrary to that, at the minimum, dy dx is 0, as we expect, and d2y dx squared is going to be positive, because our slope is becoming more and more positive as we're in this part of the curve. Our slope is negative, becomes 0, and then becomes positive. So it's becoming more and more positive at the minimum. Now, before we jump into this question, I'm going to switch to GeoGebra and show you what I've just been talking about play out. Now, we have a positive cubic function here, and I have the blue line as the tangent line, and I have my point of contact here. But I know this is a positive cubic because it is rising up to the right and it has a general cubic shape. So it's important we can spot what type of function we're looking at in a graph, but this is a positive cubic function. Now, keep track of the slope here. This is our derivative. This is dy dx for different values of x as I move my cursor around. So keep an eye on what the slope is doing as we move across, as we bring our x values to the right. So to begin with, we start off with a slope of, we'll say, around 10. And then as we move forward, what's happening to the slope as we go up towards the maximum point? It's becoming more negative. So the slope is still positive, but it's becoming more negative as we head up towards the maximum point where our dy dx is 0. We go over the hill and we would have our dy dx is equal to 0, but it's not playing along. So dy dx is equal to 0 at the top of our hill, but our slope is becoming more and more negative all the time. It's now negative, it's coming down, it's becoming more and more negative as we go down towards the point of inflection. And then at around the point of inflection, we have a slope of minus 2.07. And now it becomes minus 2.06, and it's actually increasing again. Our slope is becoming more positive as we come down towards the minimum. We come down towards the minimum. We end up with, it'll play this time. At our minimum, our slope is 0, but critically also, our rate of change of our slope is positive. We had a negative slope up at our point of inflection here, and then we come down past our point of inflection and we're becoming more and more positive with our slope. At the minimum, we have our slope of 0, and then we keep on going and we're becoming more and more positive as we go on. So the rate of change of our slope is positive around here. So that's what we've been talking about so far. Now we're going to switch back to our normal page, so the screen is going to get darker. Now let's look at this in practice. So we want to find the maximum and minimum points of our function here. Y is equal to x cubed and so on. Now, I could have also been asked to find the stationary points and state the nature of those points. I could be asked to find the turning points and find the nature of those points. I need to know that those different ways of asking the question are possible. But I know that if I'm asked for the maximum and the minimum, I'm going to use differentiation. If I had a quadratic question I was asked about, then I would be able to use completing the square if I wanted to, but generally our differentiation will be much quicker. So let's put this into practice. If I see maximum or minimum, I'm dealing with getting dy dx is equal to 0, and then seeing what the 2y dx squared is doing at that point. So I get dy dx, everything's already in power notation, so I don't need to do any changes. I get 3x squared minus 6x minus 9. And I want to know my maximum and minimum, so that means dy dx is going to be equal to 0. So I have a quadratic here, and I want to find the values for which this is equal to 0. So this is my derivative function now. This was my original function. This is the slope of the tangent to the curve function. So I see that I have a common factor of 3 that I can divide out on both sides. Again, we would never divide out a common factor of x, but we can divide out common factors of numbers to make the numbers nicer for us to deal with. I factorize this and I get x minus 3 on x plus 1. So x minus 3 is equal to 0 and x plus 1 is equal to 0. We're just factorizing a quadratic as normal. Is equal to 1. And what else do I need to find? Well, I'm asked about maximum and minimum points. A point is a word that means I have to get coordinates. So I'm now going to have to go in to my original function and find the coordinates of my maximum and minimum, the y values for my maximum and minimum. So I write down my function so I don't make any mistakes. And I sub in, there's an error there, -1, 3 cubed minus 3 squared, oh yeah, minus 9 on 3 plus 1, I'm going to do that for both. Now I have my 2 points. I need to figure out which of them is a maximum and which of them is a minimum. Now there is an obvious way that you can figure it out in this particular case because you know what a positive cubic looks like and you can see which one of them is physically higher. This is our y coordinate. So this one is higher than this one, therefore, this is going to be the maximum and this is going to be the minimum. That's fine. We still need to know the method in general and we should always practice the method out. So I need to find d2y dx squared. Sorry, I need to find d2y dx squared, so I'm going to write dy dx and then take the derivative again. 3x squared minus 6x minus 9 is my dy dx, so I need to get the second derivative. And I want to know at x is 3 and x is minus 1, what are those values? So d2y dx squared, I should say, at x is equal to 3 is equal to 6 on 3 minus 6 is equal to 12. Which is greater than 0, therefore minimum. And do likewise for minus 1. So when we do that, we get that our second derivative is negative for x is minus 1, therefore it is a maximum point. We write down our 2 points and clearly state which are minimum and maximum. There's one final point to highlight to you that is a trick that has come up on the exam papers, and there's no other word for it than a trick, but you need to be aware of it. If they give you an interval over which the function is supposed to be defined, so here I just gave you a function and I asked you for the maximum and minimum, this is exactly what you do under that circumstance. If they give you an interval, as in they say that x is greater than 1, greater than or equal to 1, less than or equal to 7, say. You need to sketch the function between those points. Because even though this should be the maximum, according to differentiation, and this should be the minimum, if they've given you an interval for the function, the maximum and minimum take on a slightly different meaning. They mean what's the highest that our function gets to and what's the lowest that our function gets to. So our minimum point would be down here over this interval, and our maximum point would be up here over this interval. Now this is a trick, and it's not particularly fair, but they have done it on the exams, so have a note to yourself in your mind. If they give you an interval that you are doing your question over, then you need to sketch the function and make sure that the dy dx maximum and minimum are actually the biggest and smallest values that the function produces in that interval. So you just need to be careful of that as an aside in this type of question. Without an interval, this is exactly what you're always going to do.